if you think about the organic reactions that we've learnt about up to now in the course, what they all have in common is that they leave the carbon skeleton alone and they just redecorate it with different functional groups. So, for example, if we start with this compound, it's got a chain of 4 carbons, and we can, for example, react it with chlorine to give you this compound, but it still has a chain of 4 carbons, and then you can convert that into this compound, and then you can convert that into this compound, and so on. So you've learnt lots of reactions, but all of them leave the actual arrangement of carbons the same. But organic chemistry, remember, is about developing an ability to construct complex, useful, important molecules from relatively simple starting materials, and often that involves not just redecorating the carbon framework but expanding it and making it into something bigger and more complicated. So an important class of organic reactions are ones which create new carbon-to-carbon bonds and therefore allow you to expand the carbon framework. So the Friedel-Craft reaction is an example of that, and it's also a kind of electrophilic substitution. So let's have a look at how it works. So here's an example of a Friedel-Craft reaction. So we've got benzene and we've got a haloalkane. And the simplest way to visualize what goes on in a Friedel-Craft reaction is to think of it as a reaction in which the halogen in the haloalkane gets replaced by the benzene ring. If you think of it that way round, it's very easy to get the structure of the product correct. Okay, so you've got your haloalkane, that keeps the structure it's got, but wherever the chlorine or bromine is, then a benzene ring gets attached instead. So the outcome of that is going to be that we'll still have this group where the haloalkane was, but instead of the chlorine, we'll now have a benzene ring attached here. And what's left from that, we've obviously got the chlorine which has been booted out from here, we've got a hydrogen which has been booted out from there, and so they will get together and give you HCl as your other product. Okay, so that's the first thing, is to make sure you get that pattern, that it, although when we come to look at the mechanism, we'll see that it's an electrophilic substitution on the benzene ring. When you're just trying to work out the products, the easy way is to think about it as a reaction in which the halogen group on the haloalkane is substituted by a benzene ring. So how do you do it? Well, you need a catalyst, because this compound is nowhere near electrophilic enough to react on its own. And the catalyst you use, interestingly, is one you're familiar with already, which is AlCl3 or FeCl3. In other words, it's a halogen carrier catalyst. So it works in the same way as it does when it's catalyzing the reaction of chlorine with benzene. So let's just remind you of how that worked. That when you had chlorine and you added the halogen carrier catalyst to it, right, let's just write out the chlorine like this, then what you get is that the AlCl3 grabs one end of that Cl2 molecule, breaks the bond heterolytically to give you AlCl4 minus, and that leaves Cl plus behind. So what's going to happen in this case is something very similar, because again the AlCl3 is just going to grab a chlorine from wherever it can, in this case from that compound. So okay, starting from that haloalkane, it's going to do that, and the pattern is exactly the same. It's going to grab that chlorine to give you AlCl4 minus, And what it leaves behind then is a carbocation with a positive charge there. Okay, so you can see the similarity that the AlCl3 is doing the same thing in both cases, just grabbing Cl-, in this case from chlorine, in this case from the haloalkane, and leaving a positive ion behind, Cl+ in that case, or this carbocation in this case. And that now is going to be your potent electrophile, because it's got a full positive charge, so it's going to be very good at attracting a pair of electrons out of the benzene ring. So once again, we'll go through the mechanism in a minute, but see if you can figure it out for yourself, because it's exactly the same as the ones you've already learnt, halogenation and nitration, once you've got the electrophile generated. Okay, so here's the benzene, here's the carbocation that's been generated by the action of the catalyst. So you know what's going to happen now. A pair of electrons is going to come out from the delocalized system, and it's going to go straight to, it's going to go straight to that positively charged atom. So that's your curly arrow showing that. And so that's going to give you an intermediate. Again, it's sort of general features of that intermediate are going to look very familiar by this point. So you have the hydrogen still attached here, but now this new alkyl group attached there as well. And here you have your what's left of your delocalized system with 4 pi electrons spread around the 5 carbons, so the positive charge has now been effectively shared out around the ring there. To restore that to being aromatic once again, we have to break that bond from carbon to hydrogen, and that will give us our organic product. It's going to look like this. It's got the benzene ring back again, and we've got the alkyl group on there, an H+. And the final step, again, we're very used to this now, is regenerating the catalyst. So we're going to take the H+ from here and the AlCl4- from there. And they're going to give you HCl, which is our second product, and restore the catalyst to its original state. So, easy mechanism to understand once you've learnt the other ones, because it's basically the same, but you just have to get used to these carbocation intermediates now being formed in this novel way. And you can see how incredibly useful this reaction is, because it allows you to add a benzene ring, in other words to add new carbons on to whatever organic structure you already have, and that's a very useful and powerful thing to be able to do. So this variation of the Friedel-Crafts reaction is called Friedel-Craft Acylation. Acylation just means adding an alkyl group on, and an alkyl group, of course, is just a carbon chain of one kind or another. So this is Friedel-Craft's Acylation, is what we've been doing here. There is another version of the Friedel-Craft reaction which you also need to know, which is called Friedel-Craft Acylation. Let's have a look at that. Friedel-Craft Acylation uses a compound that looks like this. So it's a bit like a haloalkane. It's got the halogen group, but instead of just being attached to a normal carbon, it's attached to a carbonyl group. Now, this is a kind of compound we haven't met before. It's called an acyl chloride. Okay, so acyl chlorides all have that in common, that they have a carbonyl group at the end of a chain, and then a chlorine attached there. And they're tremendously useful compounds because they're very reactive in lots of different ways, not just in this reaction, and we'll come back to them in quite different sort of reactions later in the year. But they're very good in Friedel-Crafts reactions too. The name of this particular one, because you've got a 3-carbon chain, it's propane, and if it was OH there, it would be propanoic acid, right, if you had COOH, but because you've got COCl instead, it's called propanoyl chloride. Okay, so that's an example of an acyl chloride, and the pattern of the Friedel-Craft reaction is exactly the same as alkylation. So you're almost not really learning a new reaction, you're just saying, well, it doesn't really matter if you've got a carbonyl group there, the outcome's the same anyway. So, same kind of catalyst, aluminium chloride or FeCl3 will do fine. And the same pattern, wherever the chlorine is, it gets replaced by a benzene ring. If you think of it like that, it's very easy to figure out what the product would be. So that bit's the same, but instead of the chlorine on the end of that, you get the benzene ring. And your other product, once again, you've got rid of the chlorine from there, you've got rid of a hydrogen from the ring, so you get HCl. So it's extremely similar to the alkylation reaction. And what it generates, you can see, is a ketone. Okay, because the carbonyl group, which did have the chlorine there, now has carbons on both sides of it. So this is a reaction which generates aromatic ketones as the product. And the mechanism is exactly the same as you've already learnt. So if you start with your propanoyl chloride and you add AlCl3, then you know what the AlCl3 is going to do, because it's always the same. It grabs Cl- from whatever it's reacting with to give you AlCl4-, and what that leaves behind this time will be this positive ion, okay, with a positive charge on that carbon. And then the rest of the mechanism is the same as before. So we've got there's the positive charge, so our curly arrow is going to make specifically for that atom. Make sure you get your curly arrows accurate. Goes for the positively charged atom, which is that one, which gives you your intermediate. Usual delocalization now just around the 5 carbons, and the 6th one has the hydrogen there, but also that group. And then it's going to spit out the hydrogen as H+ by pulling that pair of electrons back into the ring. So that gives you your organic product, which is that, and H+. And the final step is this H+ reacting with the AlCl4- to give you HCl, which is your other product, and restore your AlCl3 catalyst. Okay, so this type of Friedel-Craft reaction is called Friedel-Craft Acylation, because what you're substituting onto the benzene ring this time is not just an alkyl group, but it's an acyl group, which is what you call something which has the carbonyl group at the junction there. So Friedel-Craft's important to learn the mechanism, but important also to practice predicting products and thinking what haloalkane you would need to make a particular desired product, because these reactions, carbon-carbon bond forming reactions, really important in synthesis.